All right, let's talk about something that feels like it's straight out of science fiction but is very, very real: quantum computing. Today, we're going to pull back the curtain on this incredibly powerful idea. We'll break down what it is, how it actually works, and why it really could change just about everything. So yeah, let's dive right in. Think about every single computer you've ever used: your phone, your laptop. Deep down, they all work on a really simple idea. Information is stored in bits that are either a 0 or a 1. It's either on or it's off. But what if that wasn't the only way? What if a computer could actually tap into the bizarre, fascinating rules of the quantum world to be both on and off and everything in between all at the same time? You see, to really wrap your head around quantum computing, you first have to accept something kind of wild. At the tiniest, most fundamental level, the universe just plays by a totally different set of rules. And I don't mean slightly different. It is a complete, fundamental shift in how reality itself operates. We tend to think about computing as just abstracts, ones and zeros, right? But it's always, always tied to a physical machine. And this quote gets right to the heart of it. Because computation is a physical process, when we learn more about physics, we get new ways to compute. So when we discovered quantum mechanics, we didn't just find some new scientific theories. We actually unlocked the blueprint for a whole new kind of computer. So just how different are these rules? Well, in our everyday world, if you flip a coin, it's pretty simple. 50% chance of heads, 50% chance of tails. The probabilities are totally separate. But in the quantum world, different possibilities can actually interfere with each other. It's wild. Every path a particle could take has something called an amplitude. You can almost picture it like the height of a wave. And just like waves in a pond, these amplitudes can add up or cancel each other out, leading to some really, really strange results. The classic example of this, and this is where things get weird, is the double slit experiment. If you fire a single particle, say an electron, at a wall with two little slits in it, something totally bizarre happens. The electron doesn't just pick one slit to go through. No, it acts as if it went through both slits simultaneously. It's like it explored multiple realities at once. And then, those different paths it took actually interfere with each other on the other side. And that interference is the whole secret. It's the key. This interference can be constructive, which makes a certain outcome more likely to happen, or it can be destructive, making an outcome less likely or even completely impossible. This incredible ability for different possibilities to literally cancel each other out, that is the source of a quantum computer's power. It's not magic, it's just a totally different kind of physics. So, the big question is, how do we actually build a computer that can take advantage of all this strangeness? Well, the answer starts with creating a brand new way to hold information, the quantum bit, or as it's better known, the qubit. So, meet the qubit. It's the quantum version of a computer bit, but instead of being stuck as either a 0 or a 1, a qubit can exist in what's called a superposition, which is just a fancy way of saying it's a combination of both 0 and 1 at the exact same time. The best analogy? Think of a spinning coin. Before it lands, is it heads or tails? Well, it's neither. It's a blend of both possibilities, and that's exactly what a qubit is. The difference here is just staggering. A classical bit is like a light switch. It's on or it's off. Simple. A qubit, on the other hand, is more like a dimmer switch. It can be all the way on, all the way off, or literally any shade in between. It can hold so much more information. That is, until you look at it or measure it. The moment you do, it has to pick a side and collapses into a definite 0 or 1. Now, there's a really common myth about quantum computers that they're super fast because they try every possible answer at once. But that's not quite it. The real genius, the real magic, is in designing an algorithm that uses that interference we talked about. The goal is to make all the paths that lead to the wrong answers interfere with each other and cancel out, while at the same time making the paths that lead to the right answer get stronger and amplify each other. That way, when you finally measure the qubits, the right answer is the one that's most likely to pop out. And it's this unique ability that lets quantum computers run these special algorithms that can solve problems that are just completely impossible for even the biggest supercomputers we have today. To get why, you kind of have to understand computer problem complexity. Some problems are, relatively easy for computers. We say their difficulty grows polynomially, which means it's manageable. But then there are the hard problems. Their difficulty grows exponentially. For these problems, adding just one more item to the list can literally double the time it takes to find a solution. These are the brick walls that classical computers just can't break through. And this, right here, is where quantum algorithms come in and completely change the game. You've got things like Shor's algorithm. It can find the factors of huge numbers exponentially faster than any classical computer. Now, why does that matter? Because basically all of our modern online security is built on the fact that factoring huge numbers is incredibly hard. This algorithm could, in theory, break most of the encryption we use every single day. Then you have Grover's algorithm, which can massively speed up searching through gigantic, unsorted piles of data. Let's just put that into perspective for a second. Trying to brute force a modern encryption key, a regular supercomputer might take well over 1,000 years. A quantum computer running Grover's algorithm could potentially get it done in under 4 minutes. I mean, just let that sink in. That is the kind of world-altering power we're talking about. Okay, so if this technology is so mind-blowingly powerful, why don't we all have quantum laptops right now? Well, as you can probably guess, actually building one of these things and controlling the quantum world is incredibly, incredibly difficult. So the single biggest enemy for a quantum computer is this thing called decoherence. A qubit's delicate superposition state is unbelievably fragile. The tiniest vibration, the slightest change in temperature from the outside world, can knock it out of its quantum state and turn it into a plain old useless classical bit. Figuring out how to shield these qubits, how to correct for the errors that are bound to happen, and then how to scale all of this up to thousands or even millions of stable qubits, these are the huge engineering challenges that scientists are working on right now. At the end of the day, quantum computing isn't just about building a faster computer. It's about creating a fundamentally new tool, a new way of thinking that's born from a much deeper understanding of how our physical reality works. And that brings us right back to where we started. Computation is physical. As we keep learning more about the universe, as we uncover new layers of physics, it leaves us with this one really amazing question to ponder. What new computers will we build next?